Hello? Can you hear me through the microphone? Thank you. They got to fix that or else, I mean, just sitting there, they still have to get in there and fix that. I didn't break it. It was broken. Okay, everybody. We started polar coordinates last time, and I'm going to do one really gory, or maybe two more examples of polar coordinates. Is that okay? So I want to do one really gory example. Okay. And what I want to consider is imagine the following rectangle. Okay? And by the way, I'm doing this example because I'm also foreshadowing centroid, the concept of centroid. So you're going to see it emerge in this example right now, but I will define it very clearly in a subsequent section. But it's a useful example to do. Okay? I want to consider a rectangle which is centered on the point x, 0, y, 0. Okay? So x0, y0 is this center of this point. Okay? And it's going to extend horizontally to x0 plus w over 2, w is the width, to x0 minus w over 2. And so this line right here is x0. And this line right here is y0, and y0 is going to and it's going to extend from y0 plus h over 2 for the height to y0 minus h over 2. And what I want you to consider is the integral over this rectangle of just the function x dA. Okay? So I pause for you right now and note that this has units length cubed. Okay? And I want you to consider also the integral over the rectangle of just dA. Okay? Now, if I were to ask you this on a test from here on out, this lower one, what would the answer be? Which is equal to? So this is h times w. We know that this is height times width. It's the area, right? You can go crazy and do all the steps. But you get to say at some point, I know that that's the area, if you know the area of the shape, okay? The other thing is not as obvious, but I'm just going to do it for you. It's not that hard either, okay? So I'm going to do it. So how do we do this? Here is the object I need to calculate. And I'm probably going to end up, well, I'll work on this side of the board, then I'll work over there. That's the object I need to calculate. The first thing I have to do is choose coordinates, okay? So you choose coordinates because of ease of choosing coordinates. That's how you choose coordinates. So how would we choose coordinates over here? I would choose Cartesian, because this is a Cartesian, this is naturally expressed and simply expressed in Cartesian coordinates. So choose coordinates, we choose Cartesian, and then choosing Cartesian, I have to choose an order, and you see it's completely symmetric, so it doesn't really matter. Maybe we'll do the x integration first and then the y integration. Is that okay? So the x integration, we'll do horizontal strips first, and then we'll do the y integration. And so, of course, the way it works is you go to the leftmost part of your domain, do the horizontal strips, bang, 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 and you realize that x, without too much ado, x goes from x0 minus h over 2 to x0 plus h over 2. I'm doing that integral first. And then y is going to go from, clearly, y0, that's not an h, that's a w. Thank you, I heard that. Thank you very much for stopping me. So it's width over 2. And then y0 minus h over 2 to y0 plus h over 2. And you see that this integral is really easy to do in Cartesian coordinates. So let's just do it. X dx is x squared over 2. And I have to evaluate that at x0 minus w over 2 and x0 plus w over 2. Okay? And then I have to integrate that with respect to y. Y goes from y0 minus h over 2 to y0 plus h over 2. I hope you're not, and I'll just draw a horizontal line here to show you this is from the stuff at the top, and that's the stuff at the bottom. Okay? Well, this is equal to, clearly this is not a function of y, right? Y'all see that? This is not a function of y. So do you mind if I pull it out of the integral? It doesn't depend on y. So it's just a constant, whatever number it is, constant with respect to the y integration. It pulls out of the integral. And so I'm going to write it. I have a 1/2 x0 plus w over 2 quantity squared minus x0 minus w over 2 quantity squared. I'm going to put that in parentheses. That's the evaluation of what's in the integral. And then, of course, what's outside is what remains is y0 minus h over 2 to y0 plus h over 2 dy. Okay? Now, this is actually kind of easy, right? x0 squared minus x0 squared, they cancel. This squared is w squared over 4 minus, and this squared is w squared over 4, so they cancel also. So the first and the last cancel. And the outside and the inside are going to give me 2 times x0 times w over 2. Okay, I'm just trying to emphasize that that's the cross term. And then minus, and then you're going to get a negative 2 times x0 times w over 2. Okay, that's just putting all the terms there, just so you see where it all goes, okay? You can do that on your own. Trust me that that's what it turns out to be. And what's this? You can do this integral quickly. It's y at the top minus y at the bottom. It's just the length of the interval. That's all that this thing is. And we know that length of that part is h over 2, is h, not h over 2. Is that okay? So this is just h. Okay? And let's work this out. I got a 2. The 2's cancel. The negatives cancel. This thing works out to x0 w times 2 divided by 2. x0 times w, that's a 1. This is going to be a 1 also. So that's 2 x0 w. And then the half is going to divide it by 2. So the whole thing comes out to x0 times w times h. Okay? And it does what I told you it was going to do. It gives me a length, which is a length cubed. I said it was going to be a length cubed. Yay. Okay, I did it right. Now, but now we've got like something neat here, right? And we can remember I've always asked you to think about these things as averages, the ratios as averages. Let's take this integral, which I just computed, divided by this integral, which you knew, like that. And what I'm left with is the integral over the domain of x dA divided by the integral over the domain of dA must have units of a length, and it's x0. It's x0. But what did I say about integrals? I said to think about them as averages. And in what sense is this an average? I have averaged the value of x over this domain, which is the average location of the shape, which is what I mean by the center of a shape. This is the center, the x center of the shape. And we will learn that this is the x component of the centroid. Okay? Now, you don't need to know that right now. I'll get into gory detail later. But I did this to do a simple integral for you, an integral that has some meaning. Had you done this with y, you would have had y0 in all of this. Okay? And had you done this with more complicated shapes, you would get the center of that shape. You would get the location of the center of the shape. In fact, this is how you go about computing the center of the shape, the centroid. Okay? That's the whole material on centroid. You'll do this in 2 dimensions, and you'll do this in 3 dimensions. But I did this problem not to do this problem. I did this problem to do another problem. Okay? I did this problem to do polar coordinates. Okay? This problem is nicey nice. It's nicey nice in Cartesian coordinates. Okay? Because it's a rectilinear shape, rectangle. Okay? What if I were to try to do this in polar coordinates? I hope this at least motivated the section on centroid for you. What if I were to try to do this in polar coordinates? Okay? Now, I'm going to make this problem a little simpler. Okay? Let me say that I wanted to let our domain be given by a square. I'm just going to do this with a square right now. And you'll see how nasty, what I'm trying to show you is how nasty it's going to turn out to be, okay? You're going to see how nasty this thing turns out for a square. And then you're going to be like, okay, I can do this for arbitrary domains. I'm sorry, this is going to be a square. The board is unerasable. Somebody's used super chalk on it. Okay, let me draw the square. I'm going to draw this point. I would like to be the point 1, 1. Okay? Now I'm not going to use units just so I can get through the problem. This is going to be the point. This is going to be x equals 2. So, and this is going to be x equals 2. Y equals 2. Okay? So we got a square whose vertices are 1, 1, 1, 2, 2, 2, 2, 1. Other way around. 1, 1, 2, 1, 2, 2, 1, 2. Okay? And I want to compute the integral over the domain, the numerator here, of x dA. And I want to make your life tough. I want to use Cartesian coordinates. Okay? Sorry, polar coordinates. Okay? I use Cartesian. Cartesian would be nice. Okay? So let's do this in polar coordinates. Why am I doing this in polar coordinates? Well, because the book does these kinds of transformations. Okay? And the book is doing it not to tell you to do it in polar coordinates. The book is doing it to show you, to make you think about how you transform between coordinate systems. Okay? That's what it's trying to do. So this is an exercise in transforming between these coordinate systems. It's not to tell you, you should be, I'm never going to give you on a test, use polar coordinates to find this integral. I'm not going to do that. I'm going to say, find this integral. And I want you to use your brain to find the integral. Okay? And that means finding all the ways that are logically consistent, that'll give you the right answer, right? And in the easiest possible manner. Okay? So, Professor Bielow's always going to work technique for finding bounds of bounds of integration. Well, first, I'm saying we're going to use polar. Okay? So I have x r dr d theta. And 9 times out of 10, 99 times out of 100, you're going to do that r integration first. Okay? Because we think of boundaries r in terms of theta, not theta in terms of r. Okay? So you're going to do this one first. And you're going to have some r minimum, which is a function of theta, and some r maximum, which is a function of theta, and then some theta minimum and theta maximum. Okay? And what I want to show you is how you get these different things. Okay? Now, I've got an x in here, And what I said before, I'm continuing that integral over here, equals, what I said before is that before I go anywhere, I have to express that x in terms of the coordinate system. And so you have to substitute what x is in terms of r and theta. And that's straight up from the transformation of coordinates. So x is equal to r times the cosine of theta. And then all of that is multiplied by r dr. And then you have to integrate that with respect to theta, the result with respect to theta. Okay. So continuing over here. What do I want to do here? Okay, I need to find r min and r max. So let me work on this. I'm going to roll this down. That wasn't too hard to write down. So what do? Remember this? Take the chalk, put it at the minimum possible r, and shoot out on an array at the minimum possible theta, which is theta equals 0. I do not penetrate my domain. Increase your theta. I do not penetrate my domain. Increase your theta. Make the sound effects. It's fun. Keeps you awake. Okay? I touch the domain. Do it again. Okay. I come into the domain. I come out of the domain. So I'd like you to still color in a little circle there and a little maybe asterisk over here. Okay? And then I'm going to do it again. Color in a little circle there. Continue that, and an asterisk. Remember, these are arrays, so these are theta equals constant slices. This is the generalization of y equals constant or x equals constant slices. And then I'm going to go here, and you know, right, in this particular instance, because it's a square and I've aligned it so nicely, you know that the ray that pierces this vertex also pierces that vertex. But if it was a rectangle, that wouldn't happen, right? Okay, unless you had just positioned it just so. Okay? And so what's going to happen here? What we're going to see is that this collection of dots, the curve on which this collection of dots exists, is going to give me the r min as a function of theta. And then the curve at which these asterisks exist is going to give me the r max as a function of theta. And I have to keep going. But notice that the curve, and this happens, the curve has what we will call a derivative discontinuity. It turns a corner. Its derivative is up, and then it goes left. Up, and then left. Derivative discontinuity. It is defined piecewise. So the way you're going to do this is you're going to do this over this area first, because this area has only one lower boundary, one r min boundary, and one r max boundary. And then you're going to go this area, which will have only one r min and one r max. So you will define it piecewise as the curves suggest. Okay? In this case, it happens to be a coincidence that both these points, so your theta strip will go from the sum of theta min, which we will find out in a second, to a theta max on this strip, and you'll do this area first, and then you'll go to this part. Okay? I'm just telling you, I mean, this is going to be an easy problem. There's nothing really that hard about it. But this is the way you break it down, and so when you deal with a harder problem, how are you going to break it down, okay? So let me say that that integral is equal to theta 0 to theta 1, which is theta, I'm changing now from theta min to theta max, theta 0 to theta 1, r min, well, no, but it's just, r0 of theta to r1 of theta. I know it sounds, you might be rolling your eyes at the notation, but I want to emphasize to you, this is the first piece of the integral over that lower triangle, and then I'm going to add, well, it's going to go from theta 1 to theta 2, and it's going to go from some other r, which I'm going to call r2 of theta, to r3 of theta. You can hate me for all this notation. But nonetheless, that's the way it's going to work out. And what this says is there's going to be some r0 of theta, which is the lower boundary over here. There's going to be some r1 of theta, which is that boundary. And then you're going to go from some theta 0, which is this slice, up to theta 1, which is this slice. That's the first integral. The second integral says you're going to go from theta 1, which is pretty clear, starting on this, the triangle is at the same theta, with the lower bound of this triangle is the upper bound of the previous. But then the r0, this is a different r, the minimum one. So I'm calling it r2 for a different r of theta. And this is going to be an r3 because it's a different r of theta. r0, r1, r2, r3. I guess I could have gone r1, r2, r3, r4. I don't know. That's what you're doing, OK? So what you need to know is what these curves are. And to get those curves, well, you have a Cartesian representation of those curves, OK? So along r1 of theta, which is the lower boundary, what we have is y is equal to 1. That's the r1 of theta. Nope, 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 nope. That's r0 of theta. Stop, stop, stop. r0, 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 r0 of theta. That's the lower one here. That's the circles over here. This is the curve, y equals 1. How do you deal with this? You have to put everything in polar coordinates. Y is equal to r sine theta. You got to memorize that, guys. It's easy enough that you can memorize it, right? You've memorized it in trig ages ago. But this, you must express r as a function of theta. So r is 1 over sine theta. And that is r0. This is how you get r0 of theta is equal to 1 over sine theta. So that's what I mean. Along the curve y equals 1, it's a constraint that constrains y to be 1. It constrains r to be 1 over sine theta. And that's what I'm calling the function r of theta is 1 over sine theta. Now, r1 is where these asterisks are. Where those asterisks are along r1 of theta is where those asterisks are. That is x equals 2. That vertical line is x equals 2, yes? Can I label r and theta on the graph? So theta is the angle of each of these strips from here to there. That's theta. R is the distance from here to here. So I'm worried if I try to label it, it's going to get so complicated that it's going to be ugly. But r is the distance from here to here. So remembering the transformation of coordinates, I'll put it in the box over here. X equals r cos theta. Y equals r sine theta. And that implies that r equals x squared plus y squared to the 1/2. And theta equals the arctan of y over x. OK? This is the transformation polar to Cartesian. This is the transformation Cartesian to polar. So you interpret it as being the distance from the origin of any point. And you interpret this as being the angle as measured from the x-axis of any point. Oh, OK. So the shooting procedure says you put your chalk on the origin, you shoot to the r minimum. Right? R minimum is along this curve. So these dots, remember I said the dots are the r minimum. If you connect the dots, that's the r minimum curve. Right? So r minimum of theta is along this curve. But I don't have it in polar form. I have it in Cartesian form. This is the curve y equals 1. So that's what I'm doing there. That's the curve y equals 1. Like, wait, I got to get it in polar form because I'm doing the whole thing in polar for some crazy reason. So y equals 1, I substitute what y is. Y is r sine theta. So that means r sine theta equals 1. That means r equals 1 over sine theta along this curve. R equals 1 over the sine of theta. OK? That's a complicated expression to say y equals 1. They're equivalent. Just one's written in polar, the other one's in Cartesian. And that's the r0 of theta. That's the lower bound of theta for that curve. Okay? Along R1 of theta, okay, x is equal to 2. Now, I know you're rolling your eyes. This is r cos theta equals 2. Therefore, R1 of theta is equal to 2 over the cosine of theta. Okay? Now, this could be very easy, right? This is a very easy step I'm about to do, okay? The question is now, what is theta min and what is theta max? So I've got these guys. I'm working just with this integral over that first triangle, okay? What is theta min and what is theta max? Well, how do you figure out theta min? Now, you can do the trigonometry of it. Right? You can look at that. You say, well, this point is a 1 and this point is 2. So it's 1 over 2. You do all that stuff. But what I want you to think about is, I wanted you to think about it in a slightly different way. Okay? The way I want you to think about it is this. I have two curves. I have two curves. I have the y equals 1 curve, the y equals 1 curve, and the x equals 2 curve. So those curves intersect at the point 2, 1 in Cartesian. I have two curves, those same two curves as represented in polar coordinates. How do I figure out their intersection in polar coordinates? I equate their polar expressions, right? If r0 of theta is 1 over sine theta and r1 of theta is 2 over cosine theta, those curves intersect where those two r's are equal. Does that make sense? Because the r as coming from here, from the lower one, has the same r as coming from the upper one. So the r's are equal over there. That's the way I want you to think about it. That's how you find that point. And so it'll amount to the same thing, but when you have more complicated expressions, it'll be more generalizable. This process is more generalizable. So to find theta min, which is what I call theta 0, okay? To find theta 0, intersect the two curves, because that's what the graph tells you. They're intersecting the two curves. So what that says is r0 at theta 0 is equal to r1 at theta 0. That's the mathematical way of saying it. It says, what does that mean? It says this lower dotted curve at theta 0 equals the upper asterisk curve at theta 0. That's all that means. But r0 at theta 0 is 1 over sine of theta 0. And r1 at theta 0 is 2 over the cosine of theta 0. And I can rearrange this a little bit, right? And that tells me the tangent of theta 0, because sine over cos is tangent, equals 1/2. Or theta 0 equals arctan of 1/2. And that's just, something you would put into a calculator, but you also remember that we had those, is that a 1, 2? No, that's not a 1, 2 root. That's whatever it is. What is the arctan of 1/2? Is it pi over 6? It can't be pi over 2. You're thinking 1 over root 2. It's pi over 6? Yeah, yes, but no. I know which triangle you're thinking of, and this is where the old man has to dust off the cobwebs. 1, 2, square root of 3. You're thinking about the 1, 2, root 3 triangle, right? 1 squared plus root 3 squared is 4. Square root of that is 2. So you're thinking 1 through root 3 triangle, where this is pi over 6, pi over 3, and a right angle, 90. But that's not what we have, right? We have a 1, 2, root 5 triangle. So although it's so I don't think that somebody can just plug that in. Is he going to plug it in here? I don't know what it is. Don't worry about it. I don't care. I really don't care, right? The point is, I'm trying to teach you the process for thinking about this. The exact answer is truly, in this instance, not relevant. So now, everybody, I got this. I got this. I got this. I don't got this. Okay? Let's think about how we get this. Well, to get this, I need this, and then this and this. Okay? So let's go. So I got theta 0, which is the arctan of 1/2. And one of my intrepid students will eventually plug it into the calculator and show me mercy and tell me what the answer is. Please. R2. So we do this whole thing again, right? R2. Those of us boys of a certain generation. Thank you. This is the minimum on this domain. Okay, and then this is the maximum on this domain, right? This plot's starting to get busy. Okay, so to get R2 of theta, note that it lies along the curve, x equals 1, right? That's the x equals 1 curve going up and down. So that's r cosine theta equals 1. So r equals 1 over the cosine of theta. R3 of theta lies, now I'm going faster, along y equals 2. And that means r equals 2 over the sine of theta. This is r3 of theta, and this is r2 of theta. So now I have those two parts of the expression. Now I have to get theta 1. Theta 1 was the intersection. Now we can just look. Where's theta 1? Well, theta 1 is the intersection of this curve with this curve, right? This is the curve R1, and this is the curve R3. So note that theta 1 lies along the intersection of R1 of theta and R3 of theta. Okay? So set them equal. R1 of theta 1 is equal to R3 of theta 1. I know there's a bit of notation here, but it's really trying to tease out the logic of what we mean by these statements, functional evaluation. Okay? So R1 of theta 1 is 2 over cosine theta 1. And R3 of theta 1 is 2 over the sine of theta 1, which says that if you solve this, it says sine of theta 1 equals cos of theta 1. And that's true when theta 1 equals 1 over, then the sine of theta 1 equals cos of theta 1. And if you have, this is a complicated nonlinear expression in general, but it's easy because we know that this is a particular case where theta 1 equals pi divided by 4, or the sine of theta 1 is 1 over the square root of 2, and cosine of theta 1 is 1 over the square root of 2. That's a special triangle. That's the one I remember. That's the one that I can remember. Okay? So now I got theta 1. And then you would do the same thing for this angle over here, because the angle theta 2 occurs at the maximum most at this point. And you would just do the intersection of those ones. Okay? And in that case, I think you can convince yourself that the tangent of theta 2 is equal to 2 in that instance. Now, would you ever do this integral this way? Never. Not in real life, except in a homework set. And you'll do it in a homework set a couple times, because it makes you adept with these transformations. Okay? That's why I'm not going to bother evaluating this integral. The purpose of this part of the class is to get adept with coordinate transformations and understanding boundaries. Okay, understanding where your boundary is. Okay. Pause. You guys held on for a while. Did you follow me, or are you just bored to tears, or is what's going on over here? Is it okay? Sir, a question. Thank you. So nice. Oh, so remember, I broke up this triangle into, sorry, this square into a triangle. That's the first integral, and into another triangle. It's the second integral. So R0 of theta was the lower one here and the outer one here. And just do the same thing. Did I call R2? Yeah, R2 of theta is this one here, and this is R3 of theta. Because it goes R2 into this one, R3 into that one. Okay. I didn't want to say min and max because I'd have two different minimaxes. So I had to kind of give them a number. Okay. This one's a little notationally heavy, but it's not actually that hard, right? I mean, there's nothing really like, oh my gosh, that was a mind-blowing thing. He just shot a ray, pierced the boundary, and then had to figure out what boundary he pierced. That's all I'm doing. Okay? Oh, I hear some nice discussion. This is good. Maybe I should give you guys a problem to. Yes? So the question is, if you have to find an integral of a function, you don't have the graph, right? So you're going to need you're going to need something. you're going to need an expression for it, okay? So let's do this without a graph. So at some level, you kind of have to be able to, for me, I always have to be able to eyeball the graph a little bit. Okay, I'm just coming up with an example right now. E.g., compute the average value of f of x and y is equal to x over the domain bounded by R. Sorry, hold on a second. I was just making up this example. R equals the cosine of theta. How's that? R equals the cosine. Cosine. R equals cosine theta. Okay? How's that? There's an example. That's an example I want you guys to try to do. Let's try. I've been talking for so long. You don't want to hear my voice right now. You're sick of my voice. Okay, let's take 3 minutes. Work amongst yourselves. This is trying to flip the classroom, right? Make you guys work amongst yourselves a little bit. Look at your friends, get to know somebody you want to know. Say hi to the person sitting beside you or in front of you. They will not bite. There you go. Or work it out yourself if you are not interested in talking to anyone. So this requires doing two different integrals, right? I'm asking you for the average value of f of xy equals x over the domain bounded by r equals cos theta. You have to actually find the area of that domain, and you have to do the integral of x with respect to the area of that domain. Hi. You don't need to get it right. You need to think about it for a couple minutes. Does anybody have a question of me? A little hint? I always like to sketch out these regions. And obviously it's hard in polar because how much experience do you have in polar? You don't have a lot yet. So the way you get experience is you got to just sketch out a bunch of regions until you have experience, right? By the way, thank you for trying this. This is good for you. Anybody want to chime in? A suggestion? Insight? Okay, so by the way, the reason I put this question on the board is by the way, it's a very easy shape, and so if you think you know what it is, you probably know what it is. Second is though, I was asked to try to give you a question that you didn't know the graph. So how about if we didn't know the graph? How do we deal with this question, right? Now, it is a circle, okay, but it's not a circle centered on the origin. But you don't need to know that to do this problem. That's the point. Okay? Okay, so thank you for struggling a little bit. I guess I got to earn my money, right? My money is doing the problems for you. Anybody want to suggest a series of steps that I should follow? Yes, sir. So the answer, I would say the beginning answer is yes, right? Yes, we need to put we need to do this in polar. Or we don't need to, but it seems very natural to, so let's put everything in polar. Now, to compute the average, I first need to compute the integral of the domain of f of xy with respect to a. And what I said was, look, this is going to be the integral from some theta min to some theta max. I'm doing this in polar. From some r min, now, by the way, I assure you that this will only have one r min, to r max. These can depend on the angle. And now I have to take f of xy, which is represented in Cartesian coordinates, and I just have to represent it in polar coordinates. So technically speaking, I would say f of r cos theta, comma, r sine theta. But that's just notationally cumbersome. It just says take this, put it in polar. X is r cosine theta. So just do that. Okay? Don't get crazy about it. Then I have to integrate r dr. Remember, you always have this r dr in polar coordinates. And then the result of that, I have to integrate with respect to theta. That'll be the numerator. Okay? And then I have to find the denominator in order to compute the average. I probably will not get to it because I'd like to do this very methodically. So now, we don't know the graph of this. But remember what I said to do with the graph, and then do it algebraically. Okay? What I said to do, let's make a hypothetical graph. What I said to do with the graph was put your chalk on the origin and then shoot out at theta equals 0. Shoot out at theta equals 0 until you pierce the domain. Okay? That will give you r min. Okay? So if you were to do that in this case, what happens? Where's the domain? Okay? Well, what that means is you evaluate, what you're doing there is saying evaluate at theta equals 0 that expression. So r at theta equals 0, so r at 0 is equal to 1. So you know that if you were to do this, you would hit r equals 1. Okay? Now, that didn't tell you what's happening at the origin just yet. And so this is going to be a little subtle thing that's going to happen here. As you increase theta, though, if I keep increasing theta, you will see that r is going to get less and less, right? Because as I increase theta, cos theta gets less, and r gets less and less and less. So this curve, whatever this curve is getting closer and closer and closer to the origin. And as I decrease theta, I'm going to actually decrease theta in this case, and I'll find that my curve gets closer and closer and closer to the origin. Now, one of the things I said is that r must always be positive. That was what I said when I introduced the transformation of coordinates. R is a true distance. R must always be positive. So you must always avoid values of theta which could make r of theta be negative. Okay? Well, quite clearly, if theta, so I need this board over here, if theta is greater than pi over 2, right? At theta equals pi over 2, cosine theta is 0. Theta greater than pi over 2, it becomes negative. Okay? R of theta is less than 0, and that's not allowed. Inadmissible. Do not allow it. I don't care what your book says. Book says, talked about the allowing theta to be. R is positive. Here's a place where r would be negative. If I took that expression literally, you stay away from it. Okay? And see what happens for all theta greater than pi over 2. When theta equals pi, cosine of theta is negative 1. Okay? And as theta increases to 3 pi over 2, cos theta is increasing back to 0. So for all angles over here, it's completely inadmissible. So this whole part of the space has no graph on it. No graph on it. Okay? But what we do know is that as theta goes to pi over 2, which is theta's up here, it's going to bring r down to 0. So we know that the graph connects here. And as theta comes to 3 pi over 2, it's going to be 0. So we know the graph connects there. And if you were just to kind of connect the dots, it looks something like that. So I've sort of sketched it and got a sense of it. Okay? So what we see now from this sketch we see that r equals 0 is part of the boundary of the domain. R equals 0 is part of the boundary of this domain. Okay? Now where am I going with this? And we must avoid theta greater than pi over 2. We must avoid theta greater than pi over 2. And in this particular example, we can say avoid theta greater than pi over 2, and then theta between pi over 2 and 3 pi over 2, from here to here. Or you could have done the integral, instead of going from 0 to 2 pi, which is one turn of the circle going this way, you could have considered the integral going from negative pi to positive pi. That's still one turn around the circle, except you're starting on the back end, right? And what you see is you got to avoid negative pi to negative pi over 2, because that's this part of the space. Then you go from negative pi over 2 to 0. That's OK, because r is positive over there. And then you go from 0 to pi over 2. That's OK, because r is positive over there. And then you can't go beyond pi over 2, because r is negative over there. So we have to avoid and theta is less than negative pi over 2. So theta is less than pi over 2, and we have to avoid these places. So theta is going to be between negative pi over 2 and positive pi over 2. And so that integral becomes, so the integral, got only a couple minutes, is equal to the integral from negative pi over 2, because I figured out my natural end of where I have to go, to positive pi over 2. R min has 0 in the domain, in the boundary, so I can put R min is equal to 0. And R max, well, R max is that shape. So it's going to go up to cosine of theta. That's, oh, see, this is R max. That's the sorry if I heard a couple of groans. The problem gave me R equals cos theta. That's my R max. So I sketched out the domain by plotting a couple of points. I made some arguments about which parts of the domain you have to avoid. Okay. I'm going to tell you this, that questions on my test will not get this complicated in general, because I really want you to think of integrating using polar coordinates on simple symmetric polar domains. That's what we really need to focus on. But nonetheless, getting adept with this will help you do other problems, okay? So this is R min is 0. R max is the cosine of theta, which the problem gave me in the first place. And then, of course, x was R cosine theta. And then I have to integrate that R dr d theta. So that is the numerator of the average I have to compute. Okay? And how do you do this? Well, cosine theta is constant with respect to integration. This is the integral of r squared with respect to r. So that's r cubed over 3. And so this is going to be the integral from negative pi over 2 to pi over 2 cosine theta. That's this one here. This is going to give me r cubed over 3, so I got a factor of 1/3. And I have to evaluate the upper bound, which is going to be cosine cubed of theta. And then I have to integrate that with respect to theta. So I have to integrate cosine to the 4th. Okay? I have to integrate cosine to the 4th. Now, that's going to be the numerator. And then I have to do the same thing again, except with the function 1 over here to get the area. Okay? To get the area, it's just integral of 1 r d theta. Okay? Now, everybody, what I've actually asked you to integrate is to find the center of this object. And I claim that the object is a circle. How do I know it's a circle? Well, a bajillion years of experience is one way I know. But another way you can tell that this is a circle, and this is not an obvious step, but you just multiply both sides of that expression by r, and you're left with r squared equals r times the cosine of theta. R squared, now you express that in Cartesian coordinates. Okay, that's x squared plus y squared. And r cos theta is just x. You bring the x over to this side. X squared minus x plus y squared is equal to 0. And you complete the square of this thing right here. Okay? Whenever you see quadratic, completing the square is like your money shot, okay? So this is going to be x squared minus x. To complete the square, you add half the coefficient square and half the coefficient of the linear term quantity squared. That's 1/2 quantity squared. And subtract 1/2 quantity squared. That's 1/4. This thing is a perfect square. This is x minus 1/2 quantity squared. And this, and then this, sorry, this is equal to 0. And I bring the 1/4 over. And so this is x minus 1/2 quantity squared plus y squared equals 1/2 quantity squared. And now you can see that this is a circle centered at x equals 1/2, y equals 0 of radius 1/2. That's why it goes through the origin. Okay?